So the first slide that is showing you, the middle one is our institution, that is NV Arts Pandurangapatki Commerce College, and the right hand side we have the review or recollection of the, if you just look at the diagram, so we know that we have a bar magnet which is north and south, north pole, south pole. Then we have a horseshoe magnet which resembles a horseshoe. So we can have a ring type magnet, we can have a disc type magnet, or a magnetic needle which points towards the north, which is a compass or magnetic needle. So all these things are known to us. Then we also know about the lodestone, that is the first magnetic material, and we know the magnetic property, how it associates with the material. So how is that the particular material gets more, less, or no magnetic properties? It all depends on the very basic structure, the diagram that we see on the left hand side, that is a atom, that is nucleus, nucleus plus charge on the nucleus and electrons revolving around the nucleus. So this green one is an orbiting electron. So electron orbits around the nucleus. So orbiting of electron around the nucleus and spinning the electron in about its own axis. These motions about orbiting about a nucleus of electron and its spin about its own axis are responsible for the magnetic properties of materials. So that is how we are going to see in this. What all we are expected to study is magnetic materials. We will just introduce you from very basic, what are magnetic materials and how the magnetic properties associated with them, and what factors make them that they are classified into diamagnetic materials, paramagnetic materials, ferromagnetic materials, broadly classified into these categories. And then we will try to see about their properties, and we can compare dia to para and ferromagnetic materials. What are the difference between the magnetization of these material types? We also look into the basic definitions of magnetic field, magnetic flux density, magnetic susceptibility, permeability. So we will just briefly introduce you to these terms, and then we will move into a very interesting Langevins theory for both diamagnetic materials and paramagnetic materials. So these are the two important derivations. So we will go mathematically, we will derive the diamagnetic Langevins theory for diamagnetic material and paramagnetic material, and we conclude, because of the results that we obtain, the the particular material is showing diamagnetic property or paramagnetic property. So we also have a quantum mechanical approach for the paramagnetic materials. That is also another derivation. So we have three important derivations in this topic. Then, so we have Curie's law, Wies theory of ferromagnetic materials, and the most important is the hysteresis, the property shown by the ferromagnetic materials, that is hysteresis. So we'll draw the BH curve and we'll try to calculate energy loss for this. All these things we'll be studying in the topic. So as I have said, all materials in the universe are to some extent magnetic in nature. All the universe, all materials that are available are magnetic to some extent. The electrons in the atom not only revolve around the nucleus but also spin about the axis. They revolve around the nucleus, they also spin about their own axis, spinning about their own axis and rotation about the nucleus. This behaves like a magnetic dipole which is associated with the loop. This produces, because of orbital motion and spin motion, there is a magnetic dipole moment. The electron will also produce magnetic dipole moment because of these two kinds of orbital motion and spin motion. The two dipole moments, that is orbital dipole moment due to orbital motion, dipole moment due to spin motion, they add up vector, both are vector quantities, they add up vectorially and a resultant magnetic moment for the electron. The magnetic dipole moment of individual electrons in the atom, there are many electrons in the atom, they all add up, all are vectors, they all add up vectorially and the resultant of them give the magnetic moment for that particular atom. So that is represented by mu r, this is the external field, this is mu, this is orbiting electron, or so in some cases it can be mu or m, magnetic moment. So what all we have seen is all the materials in the universe are magnetic in nature. Electrons in the atom, they show two types of motion. One is revolving around the nucleus, that is orbital motion, spinning about own axis, which is the cause for the magnetic properties. Then the resultant of the two and resultant of all the magnetic moments of electrons, they add up. So we get a magnetic moment in a mu in one particular direction, which is inclined to the direction of field. Based on this, we have the material. So we'll just slightly go back, just have a look at this. When a material is placed within a magnetic field, the magnetic force of what happens is, when a material is placed in magnetic field, it is affected, the electrons of the material are affected. However, materials can show different reactions for the external magnetic field. So external magnetic field, when we place a substance or material, its electrons behave differently. So this reaction, it depends on this reaction behavior of electron when placed in an external magnetic field depends on number of factors, of which they may be atomic, molecular structure of material, and net magnetic moment associated with the atoms. The magnetic moments associated with atoms have three origins, three contributions are there for the total magnetic moment of an atom. So these are electron, orbiting electron, and spin. First one is orbital motion of electron, second one is spin motion of electron, the third one is very important. When an atom is placed in an external field, the electron orbital motion changes. There is a change in orbital motion caused by external magnetic field. These three components add up to give net magnetic moment. In most of the atoms, electrons are in pairs. So in most of the atoms, electrons are in pairs. If the electrons are in pair, then according to Pauli's exclusion principle, we know that one electron will have spin up and other electron will have spin down. So in most of the cases, electrons occur in pair. If an electron is in pair, then its spin will be in opposite direction. One will be up, other will be down. Otherwise, two parallel spins, two spin with up or two spin down will not be allowed according to Pauli's exclusion principle. So electrons in pair spin in opposite directions. So when electrons are paired, their opposite spins cancel their magnetic moments. So net magnetic moment will be zero. If the electrons in an atom are in pair, then the spin one will be up, another will be down. So net magnetic moment of such atoms where all the electrons are paired will have net magnetic moment zero, because the spins cancel each other. Therefore, there is no net magnetic moment. Alternately, there are some materials with some unpaired electrons. In some other materials, there is an unpaired electron. There exists an unpaired electron which contributes to the net magnetic moment. Therefore, when placed in external magnetic field, that will react. Alternatively, materials with some unpaired electrons will have net magnetic moment and will react more to the external field. They show some response for the external magnetic field in which the material is placed. Based on these factors, whether the electrons are whether the particular atom is having all the electrons as paired or some electrons as unpaired, based on this factor, the materials can be classified as diamagnetic materials, paramagnetic materials, ferromagnetic materials, or ferrimagnetic materials. So this is how we are going to see their classification. So this is what I was talking about, the types. So electron pairing in an atom. See, electron pairing in an atom. If there are, see, in the orbit, all the electrons are paired. See, first, that is, one will be up spin, another is the down spin, other is up, down, up, down. So in this kind of material, if all the electrons are paired, because of Pauli's exclusion principle, both cannot be up or both cannot be down. That is not allowed. So two identical electrons are not allowed. So spin up and spin down can be two different electrons. So such pairing, if there is all the electrons are paired, so there is no unpaired electron, then this kind of material will have zero magnetic moment, and this kind of magnetic moment material is called a diamagnetic material. And when same magnetic material is placed in an external magnetic field, a magnetic field B is applied, the dipoles are arranged in a magnetic field is induced in this. Without magnetic field, all are paired. So therefore net magnetic moment is zero. So when external magnetic field is applied, these kind of materials, they get induced magnetic field, and the direction of magnetic field will be opposite to the external field. This is known as anti-parallel. Again, if the induced magnetic field is in the direction of opposite to the applied field, that kind of materials are called diamagnetic. So diamagnetic materials are all the electrons are paired, net magnetic moment is zero. When placed in external magnetic field, they align themselves in a direction opposite to the induced field or the applied field. And if a magnet is placed, magnetic material is brought near this kind of material, then there is a weak repulsion is there. These materials are, these means diamagnetic materials are repelled from the magnet, and they are align themselves in opposite direction. They are all have paired electrons, and the most important property of diamagnetic material is, if a diamagnetic material is placed in a magnetic field, then the lines of force are pushed outside the material. They are not allowed to pass through the material. So the lines of force, magnetic lines of force, pushed outside the materials. That is also a very important property which is used in superconductors. That is known as Meissner effect, expulsion of lines of force from the center of a material. And this kind of behavior is possible with diamagnetic materials. Similarly, if a material has at least one unpaired electron, then that kind of material is paramagnetic. If all are paired, diamagnetic. If few are unpaired, then paramagnetic. Then when a paramagnetic material is placed in an external field, the dipoles align parallel to the direction of field. They align parallel to the applied field. So diamagnetic materials align anti-parallel, that is opposite to the induced field. And when placed in a magnetic field, the paramagnetic materials are attracted by the magnetic, and when placed in magnetic field, the paramagnetic materials allow the lines of force to pass through them, or there is a concentration of lines of force through the material. And when compared to ferromagnetic materials, the intensity, more number of unpaired electrons are there, they align parallel to the field, the attraction is very strong for ferromagnetic compared to paramagnetic, and concentration of lines of force is also high. So almost similar properties for ferromagnetic, but the intensity is more, very strong attraction, very strongly bending of lines of force, allowing them to pass through it, and large number of unpaired electrons, they characterize the ferromagnetic material. So for diamagnetic, no unpaired electrons, all are paired, so net magnetic moment is zero. When placed in magnetic field, they align themselves, the dipoles align themselves in a direction opposite to the induced field, and when brought near the magnet, they show repulsion. When placed in magnetic field, diamagnetic materials, they repel, or they do not allow the magnetic lines of force to pass through them. So these are the basic properties of diamagnetic, paramagnetic, ferromagnetic. So I will show some more slides for this. Same properties, some are important. So same thing once again, I'll showing by some other slide. Just want to repeat. See, diamagnetic, paramagnetic, and ferromagnetic materials. So you can compare them with a table. So when placed in a magnetic field, so the diamagnetic properties, they show repulsion. If there is attraction, they are paramagnetic materials. If the attraction is very strong, then they are ferromagnetic materials. When in diamagnetic material is placed between the pole pieces, then it is suspended perpendicular to this direction of lines of force. If the lines of force are going from north to south, then the material will stand perpendicular to this. And if it is a paramagnetic material, then it stands parallel. So it should be parallel to these lines of force. So ferromagnetic material also stands parallel to the lines of force. Only diamagnetic material will stand perpendicular to the lines of force. So if the diamagnetic material is a liquid, it can be a solid, liquid, or gas. So if the diamagnetic material is liquid, and if you place on pole pieces, these are the north and south, two magnetic poles, and if you place the liquid, diamagnetic liquid, in a watch glass, in some container, then if it is a diamagnetic material, then it will show a dip, and on either side there is a rise in the height of the liquid, and at the center, so there will be a dip. So if it is paramagnetic, it is reverse. So there will be a rise at the center, on either sides the height of will decrease. If a ferromagnetic or paramagnetic liquid is placed on pole pieces of electromagnetic in a glass container, so we can observe that at the center there is a rise. For ferromagnetic, rise will be more. For paramagnetic, rise will be less. On either sides, it will decrease. For diamagnetic, it is reverse. So middle, it will be a dip. So same thing, diamagnetic liquid, there will be a dip in the middle. On either sides, it will rise if it is placed on a watch glass placed on pole pieces, north, south. Similarly, paramagnetic material, north, south, if it is placed in a watch glass, at the center, it will rise. For this, it will center, there will be a dip. So, if a diamagnetic material is suspended, then it stands perpendicular to the lines of force. If it is paramagnetic or ferromagnetic, it will stand parallel to the lines of force. This is what we have seen. So another important property that is seen is if it is a diamagnetic liquid and if it is placed in a U tube, so a tube of U shape, if a diamagnetic liquid is filled and one of the arms is placed between the pole pieces, then if it is diamagnetic, then the level or height will fall in this arm which is placed in a magnetic field. So that is the characteristic of diamagnetic material. So if it is paramagnetic, then it should rise. Same diagram I am showing, but it should rise. If paramagnetic and ferromagnetic material, the level placed in the U tube of a paramagnetic material will rise. For diamagnetic, it will fall. Again, you can see that the diamagnetic materials, when no external field is applied, so then they will look like this. If you apply magnetic field, then the dipoles are arranged in a direction opposite to this. That is, field is induced in a direction opposite to this. And when you remove the field, once again the dipole moment is zero, because all the electrons are paired. So before field it is zero, after field it is zero. Only when it is placed in external field, the induced field or all the dipoles will be arranged in a direction opposite to this. If it is a diamagnetic material, the popular diamagnetic material is bismuth, zinc, copper, and many other materials. If it is a paramagnetic, then because of unpaired, there will be some dipoles randomly oriented. And if you place it in an external magnetic field, all the dipole moments will be aligned in a direction parallel to the applied field. And if you remove, some of them will be there, but their orientation will become random. For example, aluminium, platinum are the examples. For ferromagnetic materials, there were many small boxes like domains which are randomly arranged. So when you place the ferromagnetic material in a external magnetic field, then all the domains are arranged in a direction parallel to the external magnetic field. That is the characteristics of ferromagnetic material. So if you remove the external magnetic field, still the orientation of the domains remain same. They do not disturb. That is, they retain the properties even when the external magnetic field is removed. So that kind of materials are called ferromagnetic materials. Example, iron, nickel, cobalt. So these are the very popular ferromagnetic materials. There is one more important property which we are going to study, that is susceptibility, which is represented by chi. It is chi, and this is negative and very less than zero. For diamagnetic materials are characterized by negative susceptibility, and susceptibility is independent of temperature. For paramagnetic materials, susceptibility is positive and it varies inversely as temperature. For ferromagnetic materials, susceptibility is very large, much greater than zero, and it is very large and inversely related to temperature. One particular point called Curie temperature. Above Curie temperature, the ferromagnetic material becomes paramagnetic. So this transition temperature is called Curie temperature. So this is the basic characteristics of ferromagnetic materials. So you can see ferromagnetic materials, these are the domains, and the dipoles in the domains are arranged randomly, this in this direction, this direction, this direction, this direction. So when you apply an external magnetic field or you place a ferromagnetic material in a ferromagnetic material in a external magnetic field, all the domains are arranged parallel to the direction of field, in the direction of field. This is the basic characteristics of ferromagnetic materials. Some definitions we'll see which are required, maybe 1 or 2 marks, 1 mark also, or sometimes write note on these terms also, you need to define them. First term that we need to understand is intensity of magnetization I. It is the ratio of magnetic moment acquired per unit volume of the specimen. I is magnetic moment. This is equal to m by v. So magnetic flux phi b, total number of lines of force per unit area, the magnetic lines of force passing through unit surface is the magnetic flux density, that is phi b. Magnetic susceptibility, just I have mentioned about this. This is chi slanting x. It is not x, it is a curly x. It is the ratio of intensity of magnetization to magnetic field. So chi is equal to I by h, or magnetizing force, magnetic field intensity at any point in the magnetic field. It is the force experienced by unit north pole placed at that point, or H is related to magnetic field. B is equal to mu naught H. Mu naught is the permeability of free space. So magnetic permeability is the ability of a material to allow the magnetic lines of force is known as permeability, that is represented by mu is equal to B by H, where B is magnetic field, H is magnetizing field. So relative permeability is mu R. The product of mu O into mu R is permeability. So mu is equal to mu O into mu R, or mu naught is equal to mu divided by mu R. So where mu naught is permeability of free space, it is a constant. Mu R is relative permeability. So these are the 4-5 terms which we need to define. Intensity of magnetization I is equal to m by v, magnetic flux phi b, susceptibility chi is equal to I by h, magnetic force H is related to magnetic field, B is equal to mu naught H, magnetic permeability mu is equal to B by H, relative permeability into mu naught, that is mu naught into mu R mu. So these are the terms that we need to know. Once again, I have made a simple table for all that we have discussed today. The properties for diamagnetic, paramagnetic and ferromagnetic materials state diamagnetic material can be solid, liquid or gas. Paramagnetic material can also be a solid, liquid or gas, whereas ferromagnetic material can only be a solid. Solids are ferromagnetic. Some solids are ferromagnetic materials. Magnetic field, diamagnetic materials are weakly repelled, paramagnetic materials attract, ferromagnetic materials attract very strongly. There is a strong attraction. When brought near magnetic field, they tend to move from high to low region, tend to move from low to high field, tend to move from low to high field. Because of that, if it is a liquid placed in watch glass, they show a dip or rise. With temperature, diamagnetic materials, there is no effect. For paramagnetic materials, there is a inverse temperature. For ferromagnetic materials, above Curie point, they become paramagnetic. Permeability, for diamagnetic, it is less than 1. For paramagnetic, it is greater than 1. For ferromagnetic, very, very high. Susceptibility for diamagnetic is negative. For paramagnetic, it is positive. For ferromagnetic, it is very, very high. Examples can be copper, silver, gold are diamagnetic. Lithium, magnesium are paramagnetic. Iron, cobalt and nickel are standard examples of ferromagnetic materials. So you have to write descriptively same points. This will provide in notes. Paramagnetic, ferromagnetic. So all these things will be provided in notes. table. So I was mentioning about periodic table. So you can see all these elements from hydrogen, lithium, sodium. Then here you have iron, cobalt, nickel, manganese. So this line is ferromagnetic materials. So I will show you this line is ferromagnetic materials. These are lanthanides and actinides. So I will show you. See, these blue ones are ferromagnetic materials, iron, cobalt, nickel. All the green are diamagnetic. Diamagnetic. These materials show a huge group shows diamagnetic material in the periodic table. So these white ones are lithium, sodium, manganese, alkali, and these elements are paramagnetic, and some are chromium is antiferromagnetic. So hydrogen is diamagnetic gas. So like this, the diamagnetic materials can be solid, liquid, or gas. Paramagnetic can also be solid, liquid, or gas, whereas ferromagnetic materials are only iron, cobalt, nickel, and manganese. So these are the exclusively solids, and ferromagnetic materials are iron, cobalt, and nickel. So thank you for today's class.